Hi, Science 10. Because of the amount of information in my first video lesson in Chapter 5, my suggestion is that you do the notes from your PowerPoint. That would be on pages 2 to 9 in your note package if you're looking at your note package. And that way it will be easier to follow as I go through the main important points in the 5.1 section talking about velocity and how we calculate it with distance over time. There will be a second lesson for 5.1 for acceleration. So to start with, we're talking about how speed is measured, usually in meters per second or kilometers per hour. You can look at certain slides I'm passing by fairly quickly. You can take your time as you look at them yourself, but I'm focusing on the main points for this video lesson. The word kinematics is studying motion. There are two types of quantities we can use to describe motion, and scalar would be just simply saying the car was going 60 kilometers per hour, so you're just looking at that value, whereas a vector quantity would include direction, so you would say that the train was going 80 kilometers per hour going east. So when you hear about a vector quantity, you may see this arrow on top of the units because it's actually needing to describe direction when you answer the question. So distance then and displacement are two different things. Distance would just be how much ground was covered as you walked, and you have some device that measures exactly how many meters you went or kilometers you went. That would be distance, whereas displacement is just where you went compared to where you started out and where you ended up. So if you look at point A and point B, distance would be the path that person traveled, whereas displacement would just be this distance from A to B, where they are compared to where they started out. So those two definitions you should know. Distance would be the path traveled. Displacement is just where you are compared to where you started off. So in this case, if you go and do a loop and the runner finishes where he started, he would actually have a 0 displacement, whereas he might have run a distance of 1 kilometers, and that would be his distance. So Eva and Alan here, displacement, they started off here at the west, they ended up at the east, so their displacement is the same, whereas their distance that they traveled would not be the same because Alan had much larger distance than Eva did. So in this little question, it says if you start here and walk 4 plus 2 plus 4 plus 2 meters, you're going to end up being or covering a distance of 12 meters, but the actual displacement would be 0 because you started off the same spot you ended. So displacement would equal 0 meters. I'm hoping you can understand the difference between distance and displacement. And I don't know why these funny symbols came out when I converted this to a PDF, but anyways, I fixed it up here on the side so you can look at this, that when you calculate displacement, we put this little arrow on top here to indicate that it's a vector quantity, and we always go from the final minus the initial position. So when you subtract those, you will get a change in displacement. That little triangle means change. So the change of displacement with the symbol on top means it's a vector quantity looking at final minus initial position. And when we use directions, we actually consider going north or going east a positive, and going west or south a negative. So if you were going east and you turned around and started going west, that would be negative. If you were going north, turned around and went south, that would be negative. North being positive, east being positive, west being negative, south being negative. So this is information used when you're doing some of your problem solving. You guys may want to write this down in your notes or take a photo of it or something, because you'll have to know these. So a couple of examples. If you are traveling 2 kilometers east, stop and travel 3 more kilometers, you can see how that would equal to positive 2 east and positive 3 east would be 5 kilometers in total. Going east makes sense. If you go 2 kilometers east and turn around and go 3 kilometers west, now you have to say that it was 2 kilometers in the positive direction and 3 kilometers in the negative direction, which gives you a total of minus 1 kilometer east, which is the same as having gone 1 kilometer west compared to where you started off with. So you can see how the signs, the symbols, or the negatives and positives work in that. So I'm not assigning all of these questions in your textbook, but I will photograph those in case you don't have your book, and I'll provide the answers to those in case you would like to look at 1 or 2 of those questions regarding distance versus displacement. But today's lesson is more about velocity, and the formula for velocity, that's simply just distance over time, which it would be the scalar quantity that we might call speed, if it's just distance over time, velocity or speed. Whereas if you are including the displacement or direction traveled, we would actually call that the vector quantity of velocity. So this one is the one we'd call velocity when you're taking into account the change in distance as a vector quantity over change in time. And so if you were just looking at the entire distance that someone traveled, you would say the amount of area covered when the distance they traveled over the time that it took them. That would be this calculating the speed in meters per second usually. And that would be the whole distance they traveled. If you were calculating velocity, you would be looking at the displacement, meaning you would look at the entire distance that you change in final position minus the initial position, and then the time that it took. So when one of the conversions, before we try some, one of the conversions that is useful is that if you're finding something in kilometers per hour, but they would like to know it in meters per second, you simply, if you're going from the kind of bigger numbers to smaller units, bigger units to smaller units, you would divide by 3.6, and that would give you the answer in meters per second. If you've got meters per second, but you're being asked it in kilometers per hour, you would multiply by 3.6. So you'll see how this trick is a very easy way to convert from one to the other, depending on which one they are asking you to state your answer in. So, for example, we've got a few examples here. Try try to draw these out if you have a lot to read and you're looking that you see that Calgary is 215 kilometers away at 3:35, and later you see that it says it's 27 kilometers away. You covered a distance of 188 kilometers between 3:35 and 5:30, which is an hour and 55 minutes. So what we're looking at is the change in distance, which is the 188 kilometers, 215 minus 27. And then you're looking at the change in time, because velocity is change in distance over change in time. And the change in time was 1 hour and 55 minutes. And one thing that we can look at here is that if you want to know how many hours that entire thing is, you can say it's the 1 hour. You have to add how many hours the 55 minutes is. So to get 55 minutes to an hour, you would say 55 minutes times 1 hour has 60 minutes. Maybe you've done these conversions before. That cancels the minutes, and you're left with 55 divided by 60, giving you an answer of 0.92. So it's 1.92 hours, so that when you do this calculation, it's 188 kilometers over 1.92 hours. So then you get your 98 kilometers per hour. And that's what they were looking for. For the second question, they were just looking for speed in meters per second. Very easy. 550 meters over 35 seconds would be 15 meters per second. And in this question with the trainers, we've got the 12 meter position and the 65 meter position, and what the timer said at both. So you're just taking the final minus initial here, 65 minus 12 over the 87 minus 1.6, and that gives you 0.76 meters per second. They are going south, so you can add the south in there. It's final minus initial. Whenever it's change in distance, it's final minus initial, change in time, final minus initial. With the Blackbird question, we're looking at, this one's kind of a tricky one. I worked it all out in meters per second because it asked for it. But the trick is that if you're just going to do it in kilometers per hour, 3,562 kilometers in 1 hour, you can skip all the work and say 3,562 kilometers per hour. When you divide by 3.6, which was my trick earlier, if you divide by 3.6, you will get the answer in meters per second. And this would be the very, very easy way to do it, is take your answer in kilometers per hour, divide by 3.6, and get your answer 989 meters per second, because they were going east. If you wanted to convert your 3,562 kilometers into meters, you would have to multiply by 1,000. So you could do that and get this number. To get your 1 hour, you could say the hour is 3,600 seconds, so that you can divide by 3,600 seconds. This definitely, the converting way is more work. I'm showing you here how do you take 1 hour and find out how many seconds it is, how I got this 3,600, because 1 hour has 60 minutes in an hour, and that way you can cancel hours. And 60, to get rid of the minutes here, you have to put 1 minute at the bottom, which has 60 seconds. So 60 times 60 here is 3,600. So that's how you would do this. But again, you do not have to do that if you just figure it out in kilometers per hour and divide by 3.6 to get your final answer of meters per second. We are going to just review this. If you've got it in kilometers per hour, you divide by 3.6, you get meters per second. Okay, so one last thing for today is looking at how this distance over time looks on a graph. So you may recall that manipulated variable, usually it's time, is over here on the x-axis, and responding variable is always on the y-axis. And so in our distance time graph, our time would be on the bottom as our manipulated variable, and our distance would be on the side as our responding variable, because you set out the time and you're measuring distance. So when you have graphs like distance times graph, this shows you that this thing is going further and further and further over time, and we're going to look at how we can calculate velocity from a distance time graph. It's interesting that if the person is got a positive sort of uphill slope, they consider that positive. If they're getting seeing a downhill slope, they consider that a negative slope. And if the slope is 0, they aren't even moving because the distance is always the same. So that would be a slope of 0. Anyway, rise over run to get slope is going to give you the actual velocity by looking at a graph, and you're just looking at subtracting 2 of the y-axis points and putting it over 2 of the x-axis points, and this is a very easy way to find velocity by looking at a distance time graph. So we start off by choosing a point, usually 0, and one other point that crosses right on the grid, and the rise would be taking whatever numbers these are at. So this would be 70 minus 0 for the rise. This is considered the rise. And the run for that same spot would be 30 minus 0. So you're just taking this rise over this run, and the 70 that it went up over the 30 across gives you the answer of 2.3 kilometers per hour, because that's our units. And this graph is a graph of something going 2.3 kilometers per hour. Now, an interesting thing about this is that if you have some other spot that you used, let's say, I don't actually see another one that crosses right on the line, but let's say it was that spot that crossed right on the grid as well. You could take that one, let's say 60 minus 0 over, this is now 25 minus 0, and 60 over 25 should give you the same thing as the other person who did it on on this spot. So on a rise over run, it really doesn't matter which spots you use. You should be able to get the exact same velocity no matter where you calculate your rise over run. The examples from here continue to practice this. So over here, it's just showing you no matter if you did the 30 over the 3 or the 50 over the 5, your answer is always going to calculate out to 10 meters per second. That's how fast this object is going in this graph. So in these examples, you can see the object is slowing down because they were going, these are velocity time graphs, how fast they're going. So they were going 40 kilometers per hour. Now, after they were going 20 kilometers per hour, 10 kilometers per hour, just so you can switch your mind to thinking about a velocity time graph, and how this one shows they're slowing down. Again, this one for velocity, if they stay at 20, they have it on cruise control, and no matter how time goes, they're still at the same speed or velocity. So that just has you thinking about that kind of a graph for a second. This one is a position over time graph, and they were at position 40, and then 20, and then 10. So they're getting, they're moving, I guess, in a negative direction over time. This one continues to be at position 20. This is also a position graph. So they are not moving at all. No matter how time goes, they are still at the same position. So a couple of little graphs there to analyze. This one, I don't know what mess this is, but this is showing you your, again, rise over run. So they said, here's 2 spots that we can use, or you can use this spot and 0, or you can use 2 different spots on the graph. So as long, it doesn't matter where you find it, but find 2 spots that you're going to use and say my rise here, 30 minus 20 is a 10. And for the same 2 spots, the run here is 6 minus 4, and that would be a 2. So 10 over 2 is 5 meters per second. You guys could try it from here and here, which would be 20 over 4, which is still going to give you 5 meters per second. So no matter what you use for your rise over run, whichever spots, you will always get the same answer for the velocity on a graph. And best fit line here, just to wrap up, is sometimes your data, the green dots here, are all over the place, and you start at 0, and you're basically going to make sure that you choose a line that's the best fit for your data and has the same amount of dots outside the line that you choose, and it's kind of showing you that you've chosen the average line. If you ever have to do a best fit line, that's how you do it. I usually take a ruler, lay it on what I think is most of the dots, and if there's a few dots outside both, on both sides, you know you're just taking the spot that's the most significant of the average line that there is. And we are wrapped up for today. We are going to work on page 1115 in your notes. Those questions, they're mostly on graphs and doing the rise over run kind of determination of velocity. And those answers will be probably videotaped for you as well, so you can see how we work through those answers on 1115.